Hello, everyone. In this video, we will discuss torsion of a space curve. Torsion of a space curve. Let us first define the normal vector. We use the normal vector to represent the direction at which a space curve is turning. But how do we choose this vector mathematically? Please refer to the following 3D space. Consider a space curve as the graph of a vector-valued function, or the graph of a moving position vector. Recall from our previous discussion that the unit tangent vector at a point is this vector that points to the direction of increasing parameter, or the direction of motion. The normal vector is a vector that is orthogonal to the unit tangent vector to the point on the space curve. But which orthogonal vector do we refer to as the main or principal normal vector and use in succeeding calculations involving space curves? Recall that the unit tangent vector is a vector-valued function that has a constant norm of equal to 1. And from our discussion of derivatives of vector-valued function, if a vector-valued function has a constant norm, then the dot product of that vector-valued function and its derivative is equal to 0. Which means these vector functions produce position vectors that are orthogonal to each other for any value of the general parameter t. Hence, we choose the derivative of the unit tangent vector as the principal normal vector. Note that this normal vector is not a unit vector just yet. In calculations where we need to emphasize or retrieve the direction information given by a normal vector, we will use the unit normal vector. In the figure, this vector of magnitude equal to 1 is the unit normal vector. Remember that a normalized unit vector is a vector divided by its norm. Hence, the unit normal vector is the normal vector divided by its norm. Its magnitude is equal to 1, and it points to the same direction as the principal normal vector. Suppose the vector-valued function is parametrized by arc length. Then the unit normal vector is given by the following formula. From our discussion of curvature of a space curve, we studied the following formulas involving unit tangent vectors. This means that the unit normal vector parametrized with respect to arc length is equal to the second derivative of the vector-valued function with respect to the arc length parameter divided by its norm. Moreover, if we use this formula of curvature, we arrive at these additional formulas for the unit normal vector. Note the relationship between the unit normal vector and curvature. The unit normal vector refers to the direction at which a space curve turns, while curvature is a scalar that measures the degree of bend of a space curve, both using the unit tangent vector as the reference. Binormal vector. It is the unit vector that is orthogonal to both the unit tangent vector and the unit normal vector. Mathematically, it is the cross product of the unit tangent and unit normal vectors. In the figure, the binormal vector is this vector orthogonal to both the unit tangent and unit normal vectors. For a space curve defined by a vector-valued function in parameter t, recall the following formulas for the unit tangent and unit normal vectors. Then the binormal vector is given by the following formula. The binormal vector is already a unit vector, which means its length is always equal to 1. Suppose the vector-valued function is parametrized by arc length. Then the binormal vector can be expressed as follows. From our discussion of curvature of a space curve, we studied the following formula involving unit tangent vectors. And from the previous page, we derived the following formula for the unit normal vector parametrized by arc length. Then it follows that the binormal vector is given by the following formula. Now if we use this formula of curvature, we arrive at an additional formula for the binormal vector. And now we are ready to discuss torsion. Recall that curvature refers to the degree of bending of a space curve from the direction of motion. Meanwhile, torsion refers to the degree of lifting of a space curve from a reference plane, specifically, the plane containing both the unit tangent and unit normal vectors. Let us show the concept of torsion in the following figure. Consider a space curve, and two small sections of this curve of equal length. For both arcs, draw the unit tangent, unit normal, and binormal vectors at each endpoint, as well as a portion of the plane containing the unit tangent and unit normal vectors. We use unit vectors instead of the original vectors to easily see the difference in directions, because all unit vectors have magnitude of equal to 1, and not be bothered by any difference in magnitude of the original vectors. Imagine the unit tangent, unit normal, and binormal vectors moving as a unit along the curve. The degree at which the unit twists or rolls to a side as the curve lifts from the plane refers to torsion. Mathematically, torsion is given by the following formula. The torsion within an arc or between its two endpoints involves the ratio of the length of the difference in unit binormal vectors to the length of the arc. And we want to know the effect or component of this vector along the direction of the unit normal vector. Because both arcs have the same length, but the first arc has greater difference in direction of binormal vectors, we can conclude that the first arc has higher torsion than the second arc. That is, we can say that the space curve has a steeper lift on the first arc rather than on the second arc. The planes along the first arc have gone through a higher degree of twisting than the planes on the second arc. For a space curve defined by a vector-valued function in terms of a general parameter t, torsion is given by the following formulas. Example: find the unit tangent, unit normal, and binormal vectors and the torsion of the following vector-valued function at any value of the parameter t and where t equals 2. Solution: we need the first derivative for the unit tangent vector. Differentiate each component. Then find the length function of this vector using the formula for the norm of a vector. The unit tangent vector is the quotient of the tangent vector and its norm. Therefore, this is the unit tangent vector to the space curve at any value of the general parameter t. Next, we compute the unit normal vector using the derivative of the unit tangent vector. Use the quotient rule. Combine the expressions in the numerator by LCD method. And then combine the x, y, and z components. And simplify using a property of fractions. and then simplify the x, y, and z components further. Now we have the derivative of the unit tangent vector, which is also the normal vector. Afterwards, find the norm of the derivative of the unit tangent vector using the formula for the norm of a vector. We can write the norm in this way because the components all have the same denominator. Simplify the numerator and the denominator using property of exponents. Factor the numerator, and then divide out a common factor and take the square root. Now we have the norm of the derivative of the unit tangent vector. The unit normal vector is the quotient of the derivative of the unit tangent vector and its norm. Substitute the required expressions and simplify using a property of fractions. Divide out common factors between the numerator and the denominator. Thus, this is the unit normal vector to the space curve at any value of the general parameter t. The binormal vector can be computed using the cross product of the unit tangent and the unit normal vectors. We can write the cross product in this way because every component of the cross product will be divided by the same factors anyway. Combine the factors in the denominator using a property of radicals, and use a formula for the cross product of two vectors. And then simplify each component of the cross product. Hence, this is the binormal vector to the space curve at any value of the general parameter t. The binormal vector in this example is a constant vector. That is, the components are constants and does not depend on the general parameter t. This means that the binormal vector is going to be the same anywhere on the space curve. We can compute torsion using the following formula involving expressions we already found. Substitute the required expressions. And then simplify. Therefore, torsion is 0, and this is going to be its value anywhere on the space curve. Because we now have the expressions for the unit tangent and unit normal vectors, we can compute their values anywhere on the space curve. Substitute t equals 2 into the expression of the unit tangent vector. Therefore, this is the unit tangent vector where t equals 2. Then substitute t equals 2 into the expression of the unit normal vector. Hence, this is the unit normal vector where t equals 2. Meanwhile, both the binormal vector and torsion will have the same value anywhere on the space curve. Finally, let us graph the space curve in 3D space. Draw the unit tangent, unit normal, and binormal vectors at the endpoints of two sections of the curve. Notice that the binormal vectors all point to the same direction, which confirms the constant binormal vector we have computed. Moreover, the portion of a plane all have the same orientation, which means the space curve does not lift with respect to the plane containing the unit tangent and unit normal vectors. The entire space curve lies on a single plane, which contains all the unit tangent and unit normal vectors to the space curve. Recall that the equation of a plane can be found using a point on the plane and a normal vector to the plane. t equals 0 corresponds to the following point on the space curve, while the binormal vector acts as a normal vector to the plane. Use the following equation of the plane. Hence, this is the equation of the plane containing the space curve. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.